Solving general chemistry problems, thermodynamics. Write out the reaction quotient for the following reaction. Well, the answer is just this. Did you get it right? And here's another. Can you calculate the value of the reaction quotient for this reaction under these conditions? The answer is 0.00593. And what about this question? The equilibrium constant for this reaction is 7.01 times 10 to the 9. With these experimental conditions, will the reaction produce more reactants, calcium carbonate for instance, or more products, more carbon dioxide as an example? Well, the answer is more calcium carbonate. So how did you do? Probably the first one made pretty good sense to you. For the second one, did you ask yourself if I had missed writing out the units for the expression? Did you think there should perhaps be a bar to the -1 after the 0.00593? What about the last one? Did you know what to do with the calcium carbonate and the water? Was mixing up gases using pressure measurements along with dissolved ions using molarity a problem for you? Did you know how to make sense of the pH measurement? You might be saying, I thought I knew how to work with these equations, but there are some things I must be missing. Let's look at how we can complete these and other types of related questions, such as the following. What is a reaction quotient? How do I write it down? How is it related to the equilibrium constant? What can it tell me about a reaction? Well, chemical reactions do occur. You gotta love the thermite reaction, especially when blowing up jack-o'-lanterns. We see chemical reactions around us continually. In fact, the process of seeing itself is a chemical reaction. The type of questions chemists want to answer is such as this. If we have a container, in this case a balloon, with a mixture of oxygen gas, hydrogen gas, and water as a gas, why, when an electric spark is fired, does a reaction to produce more water proceed consuming the oxygen and hydrogen? Why doesn't the water break apart into hydrogen and oxygen gas? Because, as perhaps you know, we can set up an electrochemical cell and do exactly that, break up water into hydrogen and oxygen gas. How do we know what conditions will allow a reaction to go forward and what conditions will cause it to go backwards? And what is going on when this reaction is at equilibrium? To explain this, I will introduce two concepts that are likely unfamiliar to you. Now, I will quickly move back to more familiar territory, but I feel it is important for you to know where that familiar territory actually comes from. We can assign to every substance a property called chemical potential. The total chemical potential inside a reaction vessel is the sum of the chemical potentials of all of the material in it. In any chemical reaction, some molecules are reacting and disappearing, while others are appearing as they are being produced. When a chemical reaction occurs, reactant molecules disappear and are transformed into product molecules. This removes the chemical potential of those reactant molecules and injects the chemical potential associated with the newly formed products. Now, this concept of potential occurs widely in science. Gravitational potential energy is something we all experience. Hold a 1 kilogram ball 1 meter above the ground, and it has gravitational potential energy equivalent to mass times the gravitational constant times height, or mgh. As it is held there, it has the potential to have that much energy converted into kinetic energy. When you release it, it drops to the ground, and as it reaches the ground, its potential energy has decreased and its kinetic energy has increased by the same amount. If the ball weighs 2 kilograms, it has twice the potential. If the 1 kilogram ball is raised to a height of 2 meters, it also has twice the potential energy. These calculations require some agreement between researchers. Where will we decide 0 to be? What is the value of the constant g? Will it ever change? What happens if I go to Mars and hold the 1 kilogram ball 1 meter off the surface? The potential is always measured relative to some reference condition. How do we choose where 0 is going to be? It is arbitrary, and we choose it based on convenience. For gravitational potential energy, we generally agree to assign 0 to the surface of the Earth, but this is only because we do not usually tunnel into the Earth when we drop a ball. We also agree on the value for g's being 9.81 meters per square second, but this is only strictly true on the surface of the Earth in very specific locations. On Mars, the surface gravity is only about 40% that of Earth's. Even on top of Mount Everest, compared to Death Valley, G would be different. Even in a comparison at sea level between the North Pole and a spot on the equator, G would be different. But once we agree on some definitions, from there we can employ this very useful tool in understanding motion in a gravitational field. A key observation is that when an object is free to move in the field, it will always do so in such a way as to minimize its potential energy. These ideas, especially this idea of a process evolving so as to minimize its potential energy, carry over into the concept of chemical potential as well. Chemical potential is the change in energy when the amount of a substance increases or decreases in a vessel. It is represented by the symbol mu. There are 4 important state functions measuring energy: Gibbs, Helmholtz, enthalpy, and internal energy. They are all related to chemical potential. By controlling different state properties, entropy, volume, pressure, and temperature, each of these energy expressions change as given by the chemical potential. Here are the 4 differential relations. Chemical potential describes how the Gibbs energy changes with changes in the amount of material when the system is held at constant temperature and pressure. When held at constant temperature and volume, the chemical potential describes how the Helmholtz energy changes. At constant entropy and pressure, it describes changes in enthalpy. And at constant entropy and volume, it describes changes in internal energy. Rewriting the differentials, we can see how to determine the change in any of the energy state functions depending upon the physical conditions our experiment controls. Now, it turns out that in the lab, temperature and pressure are the easiest to control when the amount of material is changing due to a reaction or if the system is open and we are adding or removing material. As such, we most often use the Gibbs energy expression. The others remain valuable in their specific area of application, but controlled temperature and pressure are the most common. Hence, in general chemistry, we focus on the Gibbs equations. Under these conditions, the chemical potential is essentially the molar Gibbs energy, how much Gibbs energy there is per mole of substance. Like other potentials, it is measured relative to some standard reference condition. If it is a gas, the reference condition is that of an ideal gas at 1 bar pressure. If it is a solvated substance, it is that of an ideal solution at 1 molar concentration. If it is a solid or a pure liquid, the reference condition is that of the pure solid or pure liquid itself. Other reference conditions may be found. For gases, a reference condition of 1 atmosphere is common, but it is an older reference condition. The suggested standard is 10 to the 5 Pascal, which equals 1 bar. The difference between bar and atmosphere is small but measurable. It is worth being aware of the reference state of data you are using. For solutions, sometimes a concentration in molal rather than molar is used. Molality is moles per kilogram rather than moles per liter. Molality is a better measure because it doesn't change with temperature. Mass doesn't change with temperature, but volume does. However, it is more difficult to be making mass measurements rather than volume measurements, so molarity remains commonly used except for precision work. 1 molal is close to 1 molar for dilute aqueous solutions at common lab temperatures, since 1 liter of water weighs about 1 kilogram. So every substance has a standard chemical potential given by mu naught. Chemical potential changes with a substance's activity. This is the second unfamiliar concept I wanted to introduce. Activity. We write mu equals mu naught plus RT ln A being the activity, or A equals the exponential of mu minus mu naught over RT. The activity concept was introduced more than a century ago to describe changes in chemical potential. It has come to be described as an effective concentration or an effective pressure, but that can be misleading. Activity is unitless. It is the ratio of, let's call it, chemical performance compared to chemical performance under the reference conditions. For solutes in a solution, we measure activity for a species I as activity of I equals concentration of I over concentration standard reference condition C0, so Ci over C naught. C is the concentration in molar if that was our choice of reference condition or the condition specified by the tabulated data we are using. For gases looking at species J, we write Activity of J is P sub J over P naught, which is just partial pressure in bar, if that was our reference state compared to the reference pressure. Now, the first thing you might notice is that our molar concentration, or partial pressure in bar, are both divided by 1 molar or 1 bar. The number itself doesn't change because it's just divided by 1, but the units do cancel out. Activity has the same numerical value as concentration or partial pressure, but just no units. The other important point is to recall that for a pure liquid or a solid, its activity is C naught over C naught. It references itself, which is just equal to 1. The activity of a solid or liquid is always just 1. The activity of a solvent is usually taken to be 1, and this is what happens to water when it is the solvent in which a reaction occurs. Again, for dilute solutions, this is a good approximation. If the reaction produces or consumes some of the solvent in the reaction, it won't change the water's chemical performance because there is so much of it that it doesn't change meaningfully. Activity changes not only with concentration or partial pressure, but also accounts for the presence of other molecules with which it may be interacting, and in so doing, altering its chemical performance. This aspect of activity has been rolled into an activity coefficient, gamma. The above equations are slightly modified to read activity of I equals gamma I Ci over C naught, and for gases, activity of J equals gamma sub J P sub J over P naught. At low concentrations and low pressures, activity coefficients are close to 1 and do not substantially change the value of the activity. But under more extreme cases, the change can be substantial and has to be considered. In general chemistry, we do not deal with activity coefficients, so they are always just 1 and have no effect on the numbers we use. In essence, we just ignore it to the point that we do not usually even discuss it, and students leave the course not realizing what has been overlooked and simplified. So how does this all look when we put it together? This is a graph of chemical potential versus a parameter we will call extent of reaction, and assign it the symbol of the Greek letter xi. When xi equals 0, it is at the start of the reaction where there is only reactants, no products are present. When xi equals 1, the reaction has proceeded to completely convert all reactants into products. Let's assume that we have a stoichiometric amount of reactants, so there are no species in excess. We could deal with the excess, but it's an unnecessary complication for this discussion. We can plot the reactant's chemical potential. It starts high at the beginning, and as the reaction proceeds, it decreases because reactants are disappearing as they convert into product molecules. The detailed shape of the curve as it decreases is complex because it not only depends upon the decreasing concentrations, but also upon the changing composition that alters the activity coefficients. Finally, however, it goes to 0 at the end when all reactants have turned into products. By contrast, the product chemical potential starts at 0 because there's no products present at the beginning, and it increases in an equally complex manner until it reaches its maximum value at the end of the reaction. The sum of these two curves is the total chemical potential of the system throughout the reaction. The slope of this curve at any point indicates the chemical driving force being exerted on the system. When the slope of the curve is negative, it means that a decrease in chemical potential will tend to drive the reaction forward. Similarly, when the slope is positive, it means that a decrease in chemical potential would tend to drive the reaction in reverse. What is interesting is that there is some point where the total chemical potential reaches a minimum. The slope of the total chemical potential curve is 0 at this point. This happens because the slope of the reactant chemical potential curve is exactly equal to the negative of the slope of the product curve. This means that any changes in the product chemical potential due to the reaction are exactly countered by changes in the reactant chemical potential. It also means that the chemical potential of the reactants is exactly equal to that of the products. This value of the extent of the reaction is the reaction equilibrium condition. So how do we express this mathematically, especially when we're talking about general chemistry? Well, we will use activity, but not activity coefficients. We will use the condition that the chemical potential of reactants and products equal each other at equilibrium. we will restrict ourselves to conditions of constant pressure and temperature so that the chemical potential for each species is just its molar Gibbs energy. One of the questions we asked at the beginning of this presentation was about the reaction which dissolved chalk, calcium carbonate, in an acidic solution. The reaction equation is calcium carbonate solid plus 2H plus aqueous is in equilibrium with calcium 2 plus aqueous, H2O liquid, and CO2 gas. At any time, the system's total chemical potential is just the sum of the chemical potential for all 5 of the reaction participants. We denote the difference in reaction chemical potential as the difference between the sum of the product's chemical potential and that of the reactants. We substitute for the chemical potential for each species and include the expression for activity. The standard chemical potential for each is a constant and is determined by the choice of standard conditions. We can reorganize the expression to bring together the standard chemical potentials and the logarithm expressions for activity. So regroup the log expressions, bring them together. Recall how the sum of a collection of logarithmic terms is the logarithm of the product of those terms. Since we are choosing to discuss the reaction in terms of constant pressure and constant temperature, we can rewrite the difference of the standard chemical potentials as the difference of the standard molar Gibbs energy terms. The overall equation is now the difference in molar Gibbs energy. Next, simplify the logarithm expression. Recall that the activity of a solid, in this case calcium carbonate, is always 1. Also, since this is a general chemistry, we will view the solvent water as being basically a pure liquid, so its activity is also just 1. We can write out the remaining activity expressions, having the concentrations and partial pressures along with all activity coefficients, which are changing continually throughout the reaction. It allows us to make this calculation at any point in the reaction. Getting all of this data would be challenging, and it would hold up our study to get a better feeling for chemical reactivity. Since this is general chemistry, we will assume the activity coefficients will always be just 1, so we can drop them out of the expression. Now our standard conditions for the remaining terms will be 1 bar for pressure or 1 molar for concentration. Since these standard conditions are both assigned the value of 1, their presence does not change the numerical value of the variable, but they do cancel out the units. We proceed by dropping out a specific reference to those standard conditions, but we must retain a variable to remind us what to insert into this expression. We still use the variables of partial pressure and concentration, but we need to remember that we just use the numbers for those variables when expressed in bar or in molar, because the units have all been canceled out, because the units in the standard condition, which we've left out in order to declutter our expression. The term in the logarithm is what we call the reaction quotient, Q. Students need to remember that it is actually an expression involving activity and includes activity coefficients. We simplify and declutter this expression by dropping out terms for solids, as they are equal to 1. We drop out expressions for solvents, since it's usually very close to 1. We remove explicit reference to the standard conditions, but do not forget to express pressures in bar and concentrations in molar. We insert numbers for the variables, but no units. Look again at this reaction progression curve. We noted several properties of the equilibrium condition that could be used to define it. A minimum in the total chemical potential, or the slope of the product and reactant chemical potentials were equal and opposite in sign, or the product and reactant chemical potentials were equal to each other. This last one turns out to be convenient and asks us to focus upon the difference between the two rather than their sum as for the total chemical potential. This is the difference between the two at this particular point in the reaction. At another point, this is the difference. Note that the difference in chemical potential is smaller, and for our restriction of constant temperature and pressure, this is also the difference in Gibbs energy. The difference is still smaller here, and still smaller here, as we ever get closer to the equilibrium condition. Now, because we define the difference as products minus reactants, the value of this difference in Gibbs energy has been negative for all of these points just discussed. Now, go over to the other side of the equilibrium point. Here is the difference at this value of the extent of reaction. However, this time the difference is positive since the products are now greater than the reactants in their chemical potential, and the difference is smaller as we get closer to equilibrium. The difference is still smaller. And once we reach the equilibrium condition, the difference between products and reactants vanishes. It goes to zero. Now, I promise to get back to familiar territory, and hopefully you can see where that is now. Much of thermodynamics aims to get to this most important equation. Delta G reaction equals delta G naught reaction plus RT ln Q. Delta G reaction tells us what the reaction is doing. If it is negative, the reaction is proceeding in the forward direction. If it is positive, the reaction is proceeding in the reverse direction. If it is zero, the reaction has reached equilibrium. At that point, Q is the equilibrium constant K. How do we calculate it? Well, we need delta G naught, a reaction of and the difference between the standard Gibbs energy of the products and the reactants. Because it is a difference, the location of what we will call zero is immaterial. The difference will always be the same. Because of this, we can use the tabulated values for the standard Gibbs energy of formation and use our old mantra of products minus reactants to obtain delta G naught for the reaction. R is the gas constant, no problem there. Just be sure to get the units right. Don't mix kilojoules and joules, for instance. T needs to be given or assumed. If the question does not say otherwise, assume 298 Kelvin for the temperature. And always use temperature in Kelvin in these kinds of questions. Then we just need Q. As before, insert the values for the given conditions. Leave out solids, liquids, and solvents by noting or assuming they have the value of 1. Put in partial pressures using just the number in bar, no units. Put in concentrations using just the number in molarity, no units. Calculate delta G reaction to know where on the extent of reaction curve the system finds itself, and you will then know which way it is moving in order to reach equilibrium. We can reach the same conclusion by comparing Q to K, the equilibrium constant. When Q is less than K, the reaction is somewhere on the purple side, and the reaction will spontaneously go forward. When Q is greater than K, the reaction is somewhere on the green side, and the reaction will spontaneously go in the reverse direction. When Q equals K, the reaction is at equilibrium. The difference in Gibbs energy between the products and reactants, delta G reaction, equals 0. Take another look at this equation. When at equilibrium, since delta G reaction equals 0, we can reorganize to find that delta G naught of reaction equals minus RT ln K. At equilibrium, Q is K. And this can be rewritten to read K equals the exponential of minus delta G naught reaction over RT. It can also be reorganized to highlight the way to compare Q and K to determine delta G reaction. Delta G naught reaction tells us how far the Gibbs energy has to evolve to reach equilibrium, where delta G reaction equals 0. And that from their standard conditions, which is the delta G naught. It also tells us how far Q has to evolve from the standard conditions, where everything is 1, so that Q is equal to 1, to reach its equilibrium value of K. So, wrap it up. Go back to the questions we looked at the beginning. First of all, just write down a reaction quotient. Everything here is a solute in an aqueous solvent. Remember, products over reactants, and don't forget to include the stoichiometry as exponents for each term. For the second expression, all species are in the gas phase. Pressures are all given in bar, and without any other instructions, we can assume that our reference standard condition is 1 bar. We put in the numbers, but the reaction quotient has no units. Remember products over reactants. Remember the stoichiometric coefficients for the exponents, and a brief calculation produces the result of 0.00593. Finally, the more complex question. We are given the equilibrium constant, and the question simply asks whether the reaction will proceed forward or backward. We need to convert the pH measurement into an H+ concentration in molarity. You should know that pH is just the negative base 10 logarithm of the H+ ion concentration. So a pH of 10 means that H+ concentration is 1.00 times 10 to the minus 10 molar. We write out Q. The solid calcium carbonate and the solvent water have activity of 1, so we don't write them into Q explicitly. The other terms come in as either a pressure or a concentration as appropriate. We just enter the numbers. The units have all cancelled out. Don't forget that the H plus term is raised to the power of 2 because of the stoichiometry. The calculation indicates with these conditions Q equals 1.50 times 10 to the 21. So Q is much larger than K. Hence, the reaction will proceed spontaneously in the reverse direction, which means it will produce more reactants. More chalk, calcium carbonate, will precipitate out of the solution. Mineralizing carbon is one of the ways proposed to sequester carbon dioxide from the atmosphere and attempting to reverse its effect as a greenhouse gas.